Hey everyone, welcome back to Control System Lectures. Let's continue our discussion on lead and lag compensators, and in this video we're going to focus specifically on designing a phase lead compensator using the root locus method. And if you haven't already watched the introduction to lead lag compensators, I'd recommend you start there first before watching this video. Alright, let's get to it. Let's say that you're designing a system and you already have a model of your open loop plant. Now you might have developed your model from your real physical system using a method called system identification, or you might have just been given a transfer function from your professor as a good example. Either way, the methods for designing a lead compensator are the same. The first thing that you need to do is determine your design requirements. These are the performance goals that you hope your system's going to meet. Things like rise time, settling time, phase margin and gain margin, damping ratio, and so on. But whatever your requirements are, you determine at this point that your open loop system can't meet them, so you decide that you need to implement a closed loop control system around this plant. And once you do that, as the control system designer, you get to choose any compensation technique that you want, as long as it meets the system requirements, and your control technique of choice is a phase lead compensator. So let's design one. Wait a second, we're getting ahead of ourselves. How in the world did we determine that we wanted phase lead and not phase lag or PID compensation or some other compensation method? Well, to answer that question, let's look at how phase lead compensators affect the root locus for your system, and then from there we can deduce which situations call for a phase lead compensator. Let me draw the root locus for a simple two-pole system, and I'll arbitrarily put one pole at -1 and one pole at -3. So we'll start the root locus by placing the poles at -1 and -3. And then we know from the video on sketching a root locus by hand that the locus exists to the left of the odd number of poles and zeros, which would be right between the two. And that when these two loci meet each other, they leave the real line at 90 degrees, and then they tend towards infinity along two asymptotes, one at 90 degrees and one at 270 degrees. And the location of where the asymptote crosses the real line is at a point called the center of gravity, or the centroid, which is simply the sum of the locations of the finite poles minus the sum of the locations of the finite zeros divided by the number of poles minus the number of zeros. And in our case, we have two poles and no zeros, so the center of gravity, or the centroid, is directly between the two of them, at -2. But what if we added a phase lead compensator to the system, and we saw how that affected the root locus? And I'll choose s plus 4 over s plus 5. And again, this is just an arbitrary lead compensator. But you can tell it's phase lead because the zero is closer to the origin than the pole. Let me redraw the root locus down here so that it's a little bit cleaner. We still have the two poles from the plant at -1 and -3, but now we've added a 0 at -4 and another pole at -5. Again, we draw the locus to the left of the odd number of poles and zeros, so it mostly looks the same so far. And we still have two lines tending towards infinity at +90 and +270 degrees since we added both a pole and a zero, so that's the same. But what's happened to the centroid? Well, the denominator is the same since we still only have two lines tending towards infinity. But in the numerator, we're subtracting an additional 5 because of the extra pole, and we're only adding an additional 4 because of the extra 0. So that means that our net gain in the numerator is -1, and that our new centroid is now at -2.5. Or as you've probably guessed by now, by adding a lead compensator, we've essentially dragged the asymptotes further into the left half plane. So now as we increase the gain of our system, the closed loop poles will follow these lines instead. So all else being equal, we've added stability to our system by moving the closed loop poles further into the left half plane. And we've done all of that with a lead compensator. Alright, so now that we've done that, you might be thinking to yourself, well, how does that help our situation? Well, typically when you use the root locus method, you usually have a position in mind where you want your dominant closed loop poles to reside. So you want to move them from some uncompensated closed loop position to some desired location that's going to allow your system to meet its requirements. Let me briefly go on a side note here and explain what a dominant pole is so that hopefully this will make a little bit more sense. If you have a system with a single pole, then the transient response to an impulse dies off based on the equation e to the minus st. And as you move that pole further into the left half plane, that impulse response is going to die off quicker since you are increasing the negative exponent in that equation, e to the minus st. And if you have a system with both poles that I've drawn here, then the transient response will die off at some combination of the two rates. And since the pole that's closer to the imaginary line is going to die off slower than the other pole, the response of the system will tend to follow that pole more than the others. And if it is much, much closer to the imaginary line than the others, then that's considered a dominant pole, and the system behaves so much like it that you can pretty much ignore the other poles and have very little error. So you can have a system with 5 poles that look like this, but since these 2 poles are much closer to the imaginary axis than the other ones, it's going to behave like a second-order system, as though those were the only 2 poles in the system. Okay, that leads me now to a side note. Why do you hope that your system behaves like a second-order system? Well, because when you're talking about performance measures like damping ratio, for example, this is only defined in the traditional sense for a second-order system. Let me explain that a little differently. When you're given your design requirements like rise time and settling time and so on, you need to convert these into a closed-loop pole location in the S-plane. For example, if you're given a rise time requirement, then the equation to determine the damping ratio and natural frequency of an undamped second-order system is this, which can be approximated by this simpler equation. And if you're given that the damping ratio needs to be 0.7, then you can solve for the natural frequency and figure out where your closed-loop poles need to be in order to meet those requirements. However, you can place those poles there with a compensator, but you can only guarantee that the system's going to meet these requirements if it's a second-order system or if it has a pair of dominant poles that makes it act like a second-order system. If it doesn't, then determining where to place your poles to make the system behave the way you want can be a bit more of an art form and possibly some iteration on the design until you're happy with the result. But that's for another video. Let's get back to designing the lead compensator. So you can see that after you've determined where you want your dominant poles to reside, then you can just go through the process of designing a compensator that places the poles there. And if the poles are to the left of the current root locus, the uncompensated root locus, then you need to add lead to move the root locus to the left. And if they're to the right, then you're going to need to add lag. And if the roots already exist on the root locus, then you don't need to move it at all, and all you have to do is pick the correct gain. Although you still might have a steady state error problem, and I'm going to discuss that in the lag compensator design video. Alright, while I was talking, I drew up this example. It's the same plant as before, with a root at -1 and -3. And again, I'll draw the root locus for this system. But I'm going to say, based on my requirements, I want my dominant poles to be where these green X's are, which is -3 on the real line and ±2 on the imaginary line. And I can tell from this that I need to add lead compensation because I need to move the roots further into the left half plane. So now at this point, designing a lead compensator is really just an exercise in trigonometry, just solving for the angles of a few triangles. Let me show you why. In order for a point to exist on the root locus, then the sum of the angles of all the poles minus the sum of the angles of all of the zeros has to equal 180 degrees. And the angle I'm talking about is the angle of the line from the open loop pole to the closed loop pole on the root locus. I'll demonstrate it real quick here with this blue dot. The angle of that first pole will be this θ1, and the angle of the second pole will be θ2. You always take it from the positive side of the real line. And we can just sum them together and we can see that they equal 180 degrees if you did out the math yourself. Since we don't have any zeros, there is no subtraction there. And the 180 degrees is expected because that point really does exist on the root locus. But let me redraw this here again. But this time I'm going to draw my desired pole location instead of an actual pole location. Now I can redraw my lines and then recalculate my two angles. The angle on the left is just 90 degrees, and the angle on the right, which I'm calling θ1, is just 90 degrees plus this angle in the triangle, which I'll call θ2. And when we add all of these angles up, we get 90 degrees plus 90 degrees plus whatever θ2 is, which is just the inverse tangent of 1, and this whole thing sums up to 225 degrees. And since 225 is not 180 degrees, we know that this point is not on the root locus. Not surprising. So how do we get it there? Well, we need to take 225 degrees and subtract 45 degrees. And we're going to do that by adding a single pole and a single zero. Remember that the zeros subtract, and this combination of a single pole and single zero is our phase lead compensator. Now at this point, I'm going to somewhat arbitrarily place my zero at -4. I'm going to explain this a little bit later. But when I do that, the angle that it makes up is 63.43 degrees. And now that I've placed this zero, the pole can only go in one specific spot, specifically the spot where it makes an angle of 18.4 degrees with the root that we want. In this case, the math works out really nicely, and the pole needs to be at -9. So my lead compensator for this particular problem would be s plus 4 over s plus 9. And if you plot the root locus using Matlab or some other technique, you'll see that it in fact does go through the points that I want. But there is one other small matter that you need to figure out what the gain is in order to actually place the roots at those specific points. And you can do it by hand using the magnitude criterion, or you can just do it in Matlab. But that's relatively straightforward and something that I'm going to cover in a future video. Alright, let's get back to that question. How in the world did I place that first zero where I did? Well, unfortunately, there isn't a hard, fast rule for placing the first zero. It is possible to place the zero too far to the left, and that's because you need to generate at least enough negative angle to bring the sum back down to 180 degrees. Also, you can move the zero too far to the right. If you do that, you're bringing the closed loop pole in the compensator along with it, and then you've messed up your dominant pole. So in this case, you have two poles exactly where you want them to be, but you also have this third pole that's closer to the imaginary axis, and that acts as your dominant pole, so the system isn't going to behave the way that you predicted it to. So we have a leftmost bound where you need a certain amount of negative angle, and you have a rightmost bound where you don't want your compensator interfering with your dominant pole. So a general rule of thumb is just to place the zero at or to the left of the second real axis open loop pole. This, however, doesn't guarantee that your overshoot requirement will be met. So this is one of the places where some iteration might be required. Okay, just a few more things to note. When you design a lead compensator this way, it doesn't ensure that the system's going to be stable, only that your desired pole locations do in fact exist on the root locus. It is possible that with higher order systems, another pole has wandered over to the right half plane and made the system go unstable. Also, this might be something that you want to try if you can't get a PID controller to work. I tend to think PID is a little bit more intuitive, and so I usually start there and then go to a lead lag compensator afterwards. And finally, there's a trade-off like in any design, that a faster responding system, which means poles are more in the left half plane, has the disadvantage of responding to noise also and other high-frequency inputs, and it's difficult to model high-frequency modes accurately. So it's hard to test without actually testing it on the real system. But now that you know the benefits and drawbacks of using a phase lead compensator, you should be better equipped to determine whether your system requires one or not. In the next video, we're going to tackle this exact same problem, but we're going to use the Bode plot instead of the root locus. If you guys have any questions or comments, leave them below and I'll do my best to answer them. Don't forget to subscribe so you don't miss any future videos. Also, you can follow me on Twitter at Brian B. Douglas. And as always, thanks for watching.